In this question, a graph is given between the time and the concentration of the reactant. Here R is the reactant, and here based on this graph we have to write the answers for the given questions. First one, we have to predict the order of the reaction. So here you can see, here when time is increasing, concentration of the reactant is decreasing from the initial concentration R0. It means here this reaction is a zero order reaction. That is the first one. Second one, what does the slope of the line indicates? So here we can see the concentration is decreasing, and here there is a negative slope because the straight line is going down. So here the slope of the line we can write like slope is equal to minus K. Here K is the rate constant of the reaction. Next one, what are the units of rate constant? So this is a zero order reaction. So in this reaction, the unit of rate constant will be mole liter raised to -1, second raised to -1. Now we are moving to the B part of this question. So it is given that a first order reaction takes 25 minutes for 25% decomposition. We have to calculate the half-life T half. Okay, so here it is given that it is taking 25 minutes for 25% decomposition. So we have the equation for the rate constant, that is K is equal to 2.303 divided by T log initial concentration, that is R0 divided by the final concentration. So here the time is given as, here it is given 25 minutes for 25% decomposition. So here time T is 25 minutes. Now here R0, here initial concentration we are taking as 100, and here the R means after 25% completion of the reaction, the remaining will be 100 minus 25, that will be 75%. Now we are going to find out the rate constant of the reaction, because here we have to calculate T half. We have the equation for T half, that is equal to 0.693 divided by K. K is the rate constant. It is not directly given in the question, so we can calculate the K value using the data given in this question. So we have this equation. We are substituting the values to find out the value for K, that is 2.303 divided by 25 log concentration, that is initial concentration is 100 divided by final concentration is 75. Now if you do this calculation, you will get the answer, that will be 0.0115 minute inverse is the rate constant of the reaction. If you know the rate constant, you can find out the T half using this equation, that is equal to 0.693 divided by K, that is 0.693 divided by 0.0115. Now you will get the answer, that is 60.2 minutes. That is the time required to finish half of the reaction. Now here the OR question is given. The rate constant for a first order reaction is given as 60 second inverse. How much time will it take to reduce the initial concentration of the reaction to 1/16th value? Okay, so here we have to calculate the time required for this particular reaction. So we have the equation, that is time T is equal to 2.303 by K log initial concentration divided by final concentration. That is, here it is given that the rate constant is 60 second inverse, means the K value is given as 60, and here the initial concentration, that is, it is given that 1/16th value it is reducing. So the R0 I am taking as 1, and R, that is the final concentration, means C, it is given that concentration of the reactant to its 1/16th value. So whatever the initial one, it's 1/16th value. So we can write T is equal to 2.303 by 60 multiplied by log of initial value I am taking as 1 and the final one I am taking as 1 by 16. So if you do this calculation, you will get the value 0.046 second. Now, the B part, write two factors that affect the rate of a chemical reaction. So we have different factors that is affecting the chemical reaction, that is the rate of the reaction. First we can write concentration of the reactant, or you can write temperature. In the reactions involving solids, you can write the surface area of the reactant. In the reactions involving gases, you can write the pressure, and commonly you can write the presence of catalyst. When the concentration of the reactant is increasing, here the number of particles per volume will increases. So the number of collisions increases, rate of reaction increases. When temperature increases, the energy of the reacting particles will increases. So the number of collisions increases, rate of reaction increases. When surface area increases, more particle will be in contact with each other, more particle will be exposed for the reaction. So the collision increases, rate of reaction increases. Next one, pressure. When pressure is increasing, the particles come closer in case of the gases. So they will collide more faster than the previous one. So the rate of reaction increases. A catalyst can increase the rate of the reaction by decreasing the activation energy of the reaction. So these are the different factors. You can write any of the two factors, you will get mark. Now write two conditions for the collision to be effective collision. The first one you can write, in order to be the collision should be effective, the collision will be effective if the reactant molecules are aligned, means the orienting in proper way. So the orientation of the reactant molecules are important, they should be proper. Second one, you can see all the collisions are not successive collisions if the reactant molecules have minimum energy that should cross the energy barrier, that is the activation energy. Then only it will lead to the chemical reaction. So the 2 points are, first one, the reactant molecule should be oriented properly. The second one, you can see the reactant molecule should possess minimum amount of energy, that is the energy of the reactant molecule should have a particular amount that will be greater than that of the equal or greater than that of the activation energy of the reaction. If the energy of the reactant molecules are less than the activation energy of the reaction, that is the collision then won't leads to the formation of the products. So the colliding molecule should have a minimum energy, that is the energy of the colliding molecule will be equal or greater than that of the activation energy of the reaction.